December 16, 1944, 5:31 a.m. Near the village of Monschau along the German-Belgian frontier, the winter darkness still clung to the Ardennes forest. Inside a temporary artillery command post, Colonel Oscar Axelson of the U.S. Army's 46th Artillery Group studied a row of sealed ammunition crates stacked quietly in the cold. He understood with absolute clarity that the choice he was about to make ran directly against explicit instructions issued from the highest Allied authorities. Beyond his position, visible through binoculars in the dim grey light, German units were assembling in force. What Axelson was witnessing was the opening phase of Adolf Hitler's final large-scale gamble in Western Europe, an assault that would later be known as the Battle of the Bulge. Along the northern edge of the coming breakthrough, the American 38th Cavalry Reconnaissance Squadron was dangerously exposed and vastly outnumbered. A voice broke the silence. "Enemy artillery barrage has begun, sir," reported Axelson's operations officer. "The 38th Cavalry is calling for immediate fire support." Axelson shifted his gaze back to the crates. Their markings were deliberately vague, but he knew exactly what they contained. Inside were T-98 rounds equipped with proximity fuses, experimental munitions whose use over land had been prohibited. The technology was so sensitive that even many senior American officers were unaware it existed. These shells were not designed to strike the ground. Instead, they detonated in mid-air, roughly 30 feet above the surface, scattering a downward storm of metal fragments. Foxholes, trenches, and shallow overhead cover cornerstones of infantry survival offered little protection against an explosion that attacked from above. "Load the VT rounds," Axelson finally said, using the deliberately misleading term variable time chosen to conceal the weapon's true nature from enemy intelligence. "Fire everything available." With that order, Axelson crossed a line few officers dared approach. In less than an hour, German troops advancing through the Ardennes would encounter a weapon they had never imagined was possible. When the first shells burst overhead, the effect was devastating. Unlike conventional artillery, which relied on impact or timed detonation, these rounds sensed proximity to the ground using miniature radio signals. Each explosion unleashed a dense cone of steel shards traveling at velocities approaching 3,000 feet per second. The lethal zone extended across an area roughly 60 yards wide, turning open terrain into a killing field. Digging deeper offered no safety. No practical field fortification could shield soldiers from fragments descending almost vertically. The fundamental geometry of battlefield survival had changed in moments. German scientists had previously dismissed the concept of such a fuse as unworkable. The engineering challenges seemed insurmountable, yet every shell fired that morning represented a triumph of American industrial science. Within the nose of each projectile sat a compact radio transmitter and receiver, engineered to endure firing forces exceeding 20,000 times the force of gravity. Despite that punishment, the device functioned flawlessly, detecting the ground below and triggering detonation at the precise height for maximum effect. In later evaluations, U.S. military analysts would rank the proximity fuse as the third most significant technological breakthrough of the Second World War, surpassed only by radar and nuclear weapons. Unlike those innovations, however, this one arrived without warning. German forces learned of its existence only as it tore through their ranks. Colonel Axelson's decision, taken in darkness under intense pressure, helped halt the German advance on the northern shoulder of the offensive. More broadly, it marked the moment when a secret technology reshaped the battlefield. From that morning forward, artillery was no longer bound to the ground. It had learned to strike from the air silently, precisely, and with terrifying efficiency. Each proximity fuse contained 4 vacuum tubes rather than the 5 sometimes cited, essentially compressing an entire radio transmitter into a volume smaller than a typical coffee cup. These devices were engineered to survive extreme accelerative and shock forces that would obliterate human tissue. The development effort had begun in 1940 and consumed roughly $1 billion in 1940s dollars, equivalent to about $15 billion today. By late 1943, US said. Factories were rolling out 40,000 proximity fuses each day, a number that would eventually rise to 70,000 daily by the end of World War II. British scientists who first observed the technology described it as one of the most astonishing scientific accomplishments of the conflict. Production figures underscored American industrial dominance. Between 1942 and 1945, exactly 22,731,481 fuses were manufactured, with 21,685,157 shipped for operational use and 388,324 reserved for testing purposes. Each unit comprised roughly 130 individual components, machined to tolerances of 1/100,000th of an inch. Assembly took place in clean rooms staffed by 110,000 workers, many of whom had no knowledge of the overall system they were constructing. Electrical power for the fuses was supplied by an ingeniously designed wind-driven generator, which only began producing current once the shell exited the barrel. A small protected propeller would unfold into the airstream, spinning to generate electricity that charged the capacitors, powering a radio circuit operating at 180-220 MHz. This design made the fuse completely inert until firing, safe to transport and handle, nearly impossible to detect, and resistant to jamming until the final seconds of flight. The first large-scale deployment of proximity fused shells against ground targets occurred at 6:18 a.m. On December 16, 1944, just 47 minutes after the German offensive began. Colonel Axelson's 46th Artillery Group acted without official orders, responding to an immediate tactical threat. Formal authorization from General Eisenhower did not arrive until December 19, and all operational restrictions were lifted by December 21. The impact of these fuses was immediate and severe. German troops advancing in pre-dawn darkness instinctively dropped into prepared foxholes when American artillery opened fire. Standard defensive procedures, drilled countless times, failed completely because the shells detonated in the air above them rather than upon ground contact. Shrapnel rained down at angles that rendered traditional foxholes ineffective. After-action reports from the 99th Infantry Division recorded extraordinary casualties among German battalions near Krinkel within the first 12 minutes of the bombardment. Medical units were quickly overwhelmed, and advancing formations were forced to step over their own dead to maintain momentum. By December 23, estimates suggested that roughly 2,000 German soldiers had been killed by proximity-fused rounds during fighting around Malmö, where artillery units effectively engaged SS forces. Some enemy troops reportedly panicked to the point of charging directly into artillery fire, shouting "Kamerad" in desperation. The psychological consequences were as significant as the physical destruction. To grasp why proximity fuses rendered conventional defensive positions obsolete, one must examine the physics of airburst explosions. A typical high-explosive shell detonating on the ground directs roughly 50% of fragments downward into the earth, 45% horizontally, and only 5% upward. In a properly dug foxhole, a soldier's survival probability from standard artillery fire was about 90%. The proximity fuse dramatically altered this scenario. When detonated at 30 feet, all fragments were projected downward or outward in a conical pattern. The lethal radius expanded from 25 yards for a ground burst to 60 yards for an airburst, with fragments striking at angles of 30 to 45 degrees perfectly aligned to penetrate trenches, foxholes, and rifle pits. Overall, the dangerous fragment area surged from 60 square feet with conventional fuses to 3,000 square feet, a 50-fold increase, making traditional field fortifications largely ineffective. This innovation represented not just a marginal improvement, but a fundamental shift in artillery application against infantry. The shells themselves were testaments to American precision manufacturing, containing miniaturized components designed to survive forces that would destroy ordinary electronics. The 4 vacuum tubes included a triode for oscillation and detection, a pentode for amplification, a thyrotron functioning as a trigger, and occasionally a diode for rectification. Each tube was specially hardened and bore almost no resemblance to its commercial counterpart. The result was a weapon that combined scientific ingenuity, industrial scale, and battlefield effectiveness, reshaping the dynamics of ground combat and demonstrating the remarkable technological capabilities achieved by the Allies during World War II. The development of the proximity fuse exemplified the pinnacle of American collaboration between scientific research and industrial capability during World War II. In August 1940, the British TISAT mission shared critical military innovations with the United States, including their early radar discoveries and the conceptual framework for the proximity fuse. Although British scientists had verified the theoretical principles, their domestic industrial infrastructure was insufficient to produce the device at scale. Recognizing the potential, the National Defense Research Committee, established in June 1940, prioritized the fuse immediately after radar development. Johns Hopkins Applied Physics Laboratory was designated as the central research hub, while American manufacturing began mobilizing to meet production demands. The technical challenges were immense. Each fuse had to endure accelerations up to 20,000 G, operate across extreme temperatures ranging from 50° F to 120° F, rotate at speeds approaching 30,000 RPM, and remain fully functional even after months of storage in environments as diverse as tropical Pacific islands and icy European depots. Codenamed Section T, the project eventually employed around 3,000 engineers and scientists. These teams innovated specialized plastics resistant to shattering under massive forces, miniature vacuum tubes capable of surviving conditions that would destroy ordinary electronics, and assembly techniques so precise that measurements were taken in 10,000ths of an inch. The first successful live test occurred on January 29, 1942, when a drone aircraft over Chesapeake Bay was destroyed by a proximity-fused shell. By August of that year, the USS Cleveland was outfitted with proximity-fused anti-aircraft rounds. The results were immediate and dramatic. Japanese aircraft losses escalated sharply. A historic demonstration occurred on January 5, 1943, when the USS Helena downed a Japanese dive bomber near Guadalcanal using just 4 proximity-fused shells. Despite their effectiveness, military authorities initially restricted their use over land due to concerns that unexploded shells could be captured by enemy forces. This limitation remained in place until the German Ardennes offensive created urgent tactical needs, compelling commanders like Colonel Axelson to authorize deployment decisions outside official policy decisions that ultimately proved highly effective. At sea, the fuse had already transformed naval warfare. Unconcerned by the risk of enemy retrieval, American ships could employ the new technology freely against Japanese aircraft. Statistical comparisons were stark. Conventional anti-aircraft fire required an average of 1,162 rounds to destroy a single aircraft, while proximity-fused shells achieved the same with only 310 rounds. By 1944, these fuses comprised just a quarter of all ammunition expended but accounted for over half of enemy aircraft destroyed. During the Battle of the Philippine Sea in June 1944, proximity-fused shells contributed to the event famously called the Great Marianas Turkey Shoot, in which Japanese losses exceeded 400 aircraft. Simultaneously, the British began using similar fuses against V-1 flying bombs. Following the D-Day landings in June 1944, anti-aircraft defenses along the English coastline saw kill rates jump from 17% to 79% in just 4 weeks. General Sir Frederick Pyle, commander of the British Anti-Aircraft Command, described the achievement as the most extraordinary scientific feat in military history. As Allied forces continued to fight on land, pressure mounted to lift restrictions on ground deployment. Commanders witnessed firsthand how proximity fuses could prevent infantry casualties, creating tension with bureaucratic limitations. The Battle of the Bulge ultimately forced the issue. German intelligence had already noted unusual losses among Luftwaffe aircraft. In October 1944, General Field Marshal Albert Kesselring's staff observed the sudden spike in aircraft downed by Allied anti-aircraft fire and recovered metal fragments marked by unusual scoring patterns, consistent with airburst detonations. Their report warned that if the technology were applied to ground artillery, it could cause devastating losses among infantry units. Despite these warnings, German command in Berlin dismissed the findings, failing to recognize the profound impact proximity fuses would continue to have on the battlefield. By that point, the device had already reshaped naval and aerial warfare, demonstrating the extraordinary results achievable when advanced scientific innovation is effectively harnessed through industrial production. Technical assessments during World War II initially concluded that achieving detonation of artillery shells in proximity to targets on the battlefield was unfeasible. American advancements in anti-aircraft defense, meanwhile, were largely credited to the integration of radar guidance and the deployment of denser gun networks. No immediate innovation was deemed necessary. However, this cautious approach would prove to be an enormous strategic advantage in the long run. German engineers had, in fact, been experimenting with proximity fuses since the early 1930s. They explored between 30 and 50 different concepts, including devices activated by sound waves from engines, electrostatic field triggers, and radio-based systems. Despite extensive research, none of these prototypes ever reached operational deployment. A 1940 directive issued by Adolf Hitler, which demanded that any project failing to achieve production readiness within 6 months be abandoned, effectively terminated the German program. The consequences of this decision were profound. During the Ardennes offensive, commonly known as the Battle of the Bulge, German forces seized roughly 20,000 proximity fuses but failed to recognize their purpose. German engineers had assumed that the enormous accelerative forces experienced during shell firing made such devices impossible. In effect, they held one of the most decisive technological advantages of the war without understanding its significance. On the American side, final assembly of proximity fuses was managed by 5 major corporations. Crosley Corporation produced 5.2 million units, Sylvania Corporation 5.7 million, RCA across 2 separate facilities, 5.9 million combined, Eastman Kodak 2.4 million, and McQueen Norris 2.9 million. Among these, Sylvania's Ipswich, Massachusetts plant emerged as the most productive single site, accounting for over a quarter of total output. At Crosley's Cincinnati facility, a workforce of 8,000 assembled as many as 16,500 fuses per day during peak periods. The factory maintained extraordinarily tight tolerances, capable of identifying defects as small as 1/15 of a thousandth of an inch. Its daily electricity consumption exceeded that of entire German cities. Temperature control was critical. Air conditioning kept conditions stable within 2 degrees to prevent thermal expansion from disrupting precision components. Despite such stringent quality measures, 28% of finished units were rejected for failing to meet specifications, a rate that would have crippled German production but was sustainable for American planners due to the sheer scale of output. In effect, the United States could afford to discard more precision parts in a single day than Germany could manufacture in an entire month. Sylvania dominated the production of miniature vacuum tubes responsible for 95% of the over 100 million units needed, with 10,000 workers distributed across 15 dedicated plants. More broadly, over 10 American companies participated in the supply chain, supported by more than 2,000 suppliers ranging from explosives manufacturers to precision engineering shops. A substantial portion of this workforce was female. At Sylvania's Ipswich site, 9,000 of the 10,000 employees were women, many drawn from surrounding communities. Working in highly controlled cleanroom environments, they assembled components under microscopes with tolerances as narrow as 20 thousandths of an inch, often performing a single repetitive task thousands of times each shift. By December 25, 1944, proximity-fused artillery was deployed along the entire Ardennes front. During the Battle of the Bulge, American forces fired approximately 200,000 shells equipped with this technology. General George S. Patton, initially skeptical of the effectiveness of these funny fuses, witnessed their impact firsthand and soon became an advocate. Reports from his Third Army indicated that between December 25 and 26, roughly 700 German soldiers were killed at Ectan as a direct result of proximity-fused shells. Patton's later assessment attributed the outcome of the battle in large part to this innovation, marking a dramatic shift for a commander who had traditionally emphasized mobile armored maneuvers over artillery. The psychological effect on German troops was significant. Interrogations of prisoners revealed widespread terror caused by shells that detonated precisely above ground level. Standard defensive measures such as foxholes, trenches, or shallow depressions, which had previously offered protection, became deadly traps. One German officer described to interrogators how the shells consistently exploded at treetop height, regardless of attempts to dig deeper, construct reinforced shelters, or disperse forces. The predictability of the explosions, precisely timed through advanced radio triggering, created a sense of inescapable threat far more intimidating than random artillery strikes. In sum, the American development and mass production of proximity fuses not only represented a technological triumph, but also demonstrated the extraordinary scale, organization, and precision of the U.S. wartime industrial effort. While German scientists had explored similar concepts for over a decade, strategic miscalculations and production constraints prevented them from turning theory into battlefield reality, illustrating the decisive interplay of innovation, industrial capacity, and operational implementation in modern warfare. The confrontation in the Hürtgen Forest, ongoing since September 1944, underwent a decisive transformation once proximity fuses were cleared for combat use on December 18th. The dense woodland, which had previously favored German defenders by offering concealment and protection from above, suddenly amplified the destructive potential of this new technology. Historically, artillery bursts among trees had inflicted serious damage, yet achieving such results deliberately with time-fused shells had been unreliable. Proximity fuses, by contrast, detonated at precisely the right altitude every time, whether above open fields or beneath the forest canopy. This created a lethal combination of steel shrapnel and splintered wood that rendered traditional field defenses almost entirely ineffective. During the initial 48 hours following the adoption of these fuses, the 4th Infantry Division's artillery units fired approximately 12,000 rounds equipped with the new technology. After-action reports highlighted a sharp rise in enemy fatalities and a noticeable decline in the effectiveness of German defensive arrangements. Medical personnel recorded wound types that had rarely been seen before. Victims exhibited deep puncture injuries concentrated on the upper body, particularly the shoulders and head, indicative of attacks from above. In effect, the battle became a practical study in the operational impact of proximity fuses. Artillery spotters noted a behavioral shift among German troops. Foxholes were abandoned in favor of seeking protection within bunkers and reinforced buildings. This adaptation inadvertently created concentrated positions, which became highly vulnerable to conventional high-explosive bombardment, producing a tactical dilemma that resisted any simple solution. The Allied campaign, known as Operation Grenade, which aimed to advance toward the Rhine River, commenced on February 23, 1945. In the first week of the operation, the Ninth Army unleashed hundreds of thousands of proximity-fused shells, demonstrating the vulnerability of German defensive positions painstakingly constructed over many months. The German High Command issued increasingly urgent directives to mitigate the impact of this new threat. On February 10th, a directive required all units to dig foxholes at least 2.5 meters deep, topped with logs no less than 30 centimeters in diameter, covered with 50 centimeters of earth. A revised order issued on February 18th further demanded that troops move exclusively through covered trenches when under artillery threat, and that all positions possess concrete or steel overhead protection. These requirements proved physically impossible to implement under combat conditions, as both the necessary materials and time were in short supply. A subsequent directive on February 26 simply instructed units to disperse to the maximum extent compatible with combat efficiency, limiting each position to no more than 2 soldiers. The capture of the Ludendorff Bridge at Remagen on March 7, 1945, illustrated both the strengths and limitations of proximity fuses. When Lieutenant Karl Timman requested artillery support using VT fuses to slow a German retreat across the bridge, the artillery commander denied the request, citing the proximity of American forces. Official U.S. Army histories document this instance, highlighting the critical need for careful coordination when employing proximity fuses to avoid friendly casualties. German efforts to develop an equivalent fuse technology exposed the vast industrial gap between the adversaries. Research resumed in 1944 at Rheinettel, and several hundred working prototypes were test-fired before the war's end. However, these remained prototypes rather than production-ready models. German engineers estimated that creating an operational production line would require the construction of 15 entirely new electronics factories, the training of 50,000 specialized personnel, and the development of previously non-existent manufacturing processes. Essential resources would have included 500 tons of refined copper per month, 50 tons of silver for electrical contacts, 2 million precision vacuum tubes, and 100,000 skilled workers merely to approach the production output achieved by the United States. Even assuming material availability, German industry lacked the precision machinery needed for mass production. American factories utilized Swiss-made microlathes with tolerances as fine as 1/118th of an inch, whereas Germany's best tools, worn after 5 years of continuous use, could achieve accuracies of only 1/118th of an inch on a good day. The stringent quality control requirements for proximity fuses alone exceeded the capabilities of German manufacturing. This disparity underscored the technological and industrial advantage the Allies held, making the proximity fuse a decisive factor in late-war artillery operations. Ironically, German scientists had grasped the principles of proximity fuses long before the Americans fully exploited them. Research into this technology had actually begun in Germany first, yet theoretical understanding alone did not guarantee battlefield dominance. The real challenge lay in transforming scientific insight into weapons that could be manufactured on a massive scale. The United States not only innovated technologically but also engineered an industrial framework capable of churning out millions of advanced munitions efficiently. Proximity fuses dramatically changed combat on multiple fronts. In Europe, they revolutionized artillery, turning conventional shelling into a far deadlier force. In the Pacific, their originally intended role shooting down enemy aircraft achieved unparalleled results. By 1945, VT-fused anti-aircraft shells were decimating Japanese planes with remarkable efficiency. The threat posed by kamikaze attacks, which could have made a potential invasion of Japan extraordinarily costly, was largely mitigated through this technology. During the Okinawa campaign, US ships equipped with proximity fuses successfully shot down 91 out of every 100 attacking aircraft, compared to just 25 out of 100 before the fuses were deployed. Admiral Willis Lee estimated that these fuses spared roughly 10,000 American lives in the Pacific theater. Every plane destroyed meant one less crashing into ships. This dual impact, highly effective against ground targets in Europe and decisive against aircraft in the Pacific, epitomized the American industrial approach: innovate, mass produce with precision, and apply widely. Germany, meanwhile, was struggling to meet even basic ammunition demands, and could not compete with an adversary placing sophisticated electronic mechanisms into shells designed for single use. Studies on the battlefield effectiveness of proximity fuses revealed a striking increase in lethality. Against ground targets, they proved 3 to 10 times more deadly than standard artillery. When confronting V-1 flying bombs, the destruction rate jumped from 24% to 79%. In naval anti-aircraft operations, the average number of rounds required to eliminate a single target dropped from more than 1,000 to roughly 300. The expanded lethal radius of fragments, up to 50 times larger than conventional shells, transformed artillery tactics. No longer did gunners need to concentrate massive volleys over a single area. Dispersed fire could achieve comparable results while conserving shells. This not only streamlined logistics but also reduced wear on gun barrels and allowed artillery units to support more troops simultaneously. General George Patton observed the operational advantages firsthand. Artillery, enhanced by proximity fuses, could deliver short, intense barrages rather than protracted preparatory bombardments, enabling infantry to advance while the enemy was still reeling. This increased tempo contributed significantly to the rapid Allied advances across Europe in 1945. Estimating enemy casualties directly attributable to proximity fuses is difficult. Claims of enormous death tolls, such as 250,000 German soldiers killed, lack concrete evidence. What is indisputable is the technology's multiplication of artillery effectiveness and its psychological effect on German troops. Most German soldiers never fully understood the source of the devastation around them. Interrogations revealed they often described attacks as mysterious tree bursts or air mines without recognizing the systematic engineering behind the phenomenon. German technical intelligence eventually acknowledged the sophistication of American fuses. Captured reports from March 1945 noted that the proximity fuse represented a 5-year leap in miniaturized electronics. Attempting to reproduce the technology would have required a complete overhaul of Germany's electronics industry, access to materials that were unavailable at the time, and at least 18 months of development and impossibility under wartime constraints. In sum, the proximity fuse exemplified a convergence of advanced science and industrial capacity. Its dual effectiveness across continents and battlefronts underscored how strategic manufacturing and technological innovation could decisively shape the outcomes of global conflict. A final operational report from the German High Command, dated May 7, 1945, emphasized the overwhelming impact of American artillery equipped with proximity-fused shells. It noted that these munitions had caused more casualties than all other weapon systems combined since the winter of 1944. German attempts to counteract the effect of these fuses had repeatedly failed, leading the report to advise an immediate halt to hostilities to prevent the complete destruction of remaining forces under the pressure of technologically superior weaponry. The development of the proximity fuse was a concentrated scientific effort, involving roughly 3% of all US physicists assigned to a single military project. This exceptional concentration of intellectual talent, integrated with industrial capability, produced output rates that astounded German planners. At Crosley Corporation alone, assembly lines could produce 500 units per hour, with workers performing precise micro-level operations thousands of times per shift. Production was continuous, operating around the clock every day of the week, including holidays such as December 25, 1944, when American personnel maintained full capacity while German troops. The supply network supporting this effort spanned the United States. Essential raw materials included copper sourced from Montana mines, silver drawn from government reserves, and advanced polymers manufactured by chemical firms that had been founded less than 3 years prior. The logistical complexity required to sustain such production mirrored the technological sophistication of the fuses themselves. By comparison, German artillery shell output in 1945 heavily depended on forced labor, producing ammunition with only a 60% acceptance rate. Widespread sabotage further reduced the effective availability of functional rounds. By March of that year, just under 1/3 of German shells operated correctly, while American VT variable time fuses demonstrated a remarkable 94% reliability despite their intricate electronic components. Beyond mere numbers, the introduction of the proximity fuse transformed the battlefield experience for combatants on both sides. American infantry gained a newfound sense of security, confident that their supporting artillery could neutralize enemies entrenched in prepared positions. German soldiers, by contrast, confronted a psychological shock. Traditional cover, such as trenches and fortifications, no longer guaranteed safety. Contemporary accounts from both American and German veterans corroborate this profound shift. Forward observers in the U.S. Army reported the ability to call in fire missions with unprecedented assurance, knowing that proximity fuses could strike hidden or fortified targets. German veterans recounted the disorienting helplessness caused by incoming shells that detonated above their positions, rendering conventional protective measures ineffective. The medical consequences were equally significant. The trajectory and dispersion of shrapnel from these fuses generated wounds unlike any previously encountered by military surgeons. Overburdened German medical facilities struggled to cope with these injuries, whereas American medical services equipped with penicillin, plasma, and other advanced treatments were better prepared, further amplifying the tactical advantage provided by proximity fuses. In essence, the proximity fuse was more than a weapon. It exemplified the integration of scientific research, industrial mobilization, and military strategy. It highlighted the systemic superiority of a nation capable of aligning innovation, production efficiency, and battlefield application into a cohesive and decisive instrument of war. The impact was both tactical and psychological, reshaping combat operations and redefining what constituted effective artillery support during the final stages of the conflict. During World War II, Germany invested heavily in ambitious wonder weapons such as the V-2 rocket, which demanded immense financial and material resources yet produced relatively limited military impact. In contrast, the United States concentrated on refining and mass-producing innovative technologies that could be deployed extensively on the battlefield. The V-2 missile program, for example, consumed roughly $2 billion in today's currency and resulted in around 9,000 casualties. By comparison, the USS Proximity Fuse initiative cost about half as much but fundamentally altered both ground artillery and anti-aircraft operations. This contrast highlights the differing philosophies in technological development. Germany pursued high-risk, revolutionary weapons, while America emphasized incremental improvements that could be manufactured and used on a massive scale. Beyond its technical impact, the proximity fuse also validated the American approach to research and development. Coordinated collaboration between scientists at Johns Hopkins University, industrial manufacturers, and military operators created a development pipeline that transformed an idea into full-scale production in under 3 years. Meanwhile, German projects were hindered by fragmented research structures, bureaucratic rivalries among branches of the military, and lack of unified direction. After the German surrender, American intelligence teams meticulously examined German work on proximity fuses. They discovered advanced theoretical designs but no practical pathway to large-scale production. German engineers understood the underlying principles but struggled to translate them into reliable manufacturing processes. The prototypes captured in 1945, while technically functional, relied on conventional vacuum tubes incapable of withstanding the intense acceleration of artillery shells. Various hardening attempts had failed to match the dependability of American models. Even if German engineers had solved these technical issues, the country's industrial capacity was insufficient to produce such devices in significant numbers. Limited proximity fuse units reached Soviet forces through Lend-Lease, but they lacked the technical documentation necessary for immediate replication. Soviet engineers spent 7 years reverse engineering the captured fuses, finally achieving domestic production by 1952, though the quality still fell short of the American wartime standard. This experience demonstrated that access to prototypes alone is insufficient. Successful manufacture requires mature industrial infrastructure, rigorous quality control, and specialized expertise developed over years. The development and deployment of the proximity fuse offer enduring insights into military innovation. First, iterative improvements on existing weapon systems can have a greater strategic effect than entirely new technologies. Although proximity fuses were essentially artillery shells, they dramatically enhanced their lethality and operational effectiveness. Second, the ability to produce weapons in large quantities can be just as critical as their technological sophistication. Germany achieved breakthroughs in jet aircraft, ballistic missiles, and advanced submarines, but could not manufacture them at scales sufficient to influence the war decisively. The United States, on the other hand, produced millions of proximity fuses, treating them as sophisticated yet expendable munitions. Third, effective industrial coordination linking scientists, engineers, manufacturers, and military operators is central to realizing a weapon's full potential. The American organizational model enabled this integration, whereas German rivalries and fragmented institutions hindered it. Finally, operational secrecy carries both advantages and costs. Limiting the use of the proximity fuse until late 1944 preserved the element of surprise, but also prolonged combat, resulting in additional Allied casualties that might have been avoided. Balancing secrecy with practical operational benefits remains a persistent challenge in the development of modern military technology. Beyond strategic and logistical considerations, proximity fuses also raise profound ethical questions. They made artillery significantly more precise, effective, and deadly. German soldiers exposed in defensive positions faced shells detonating above them at calculated heights, leaving little room for traditional forms of combat maneuver or protection. The technology mechanized killing, turning it into a mathematically exact process, yet, paradoxically, proximity fuses also helped shorten the war. By eliminating enemy divisions more efficiently, they indirectly reduced the number of forces defending concentration camps, thereby accelerating the liberation of Nazi victims. In this sense, a weapon that maximized battlefield lethality simultaneously contributed to ending atrocities more quickly. Admiral Lewis Strauss recognized the profound moral and strategic dimensions of wartime technological advances, particularly the development of the proximity fuse, which he considered one of the innovations most crucial to Allied victory. American soldiers returning from the front wrestled with similar complexities. They appreciated innovations that reduced the risk to their own forces, yet they were unsettled by the lethal efficiency these technologies introduced. Reports describe encounters with German defensive positions where airburst artillery had killed entire units almost instantaneously, a method of warfare that largely eliminated individual agency in the act of killing. The proximity fuse represented more than a singular weapon advantage. It was a tangible demonstration of the United States' capacity to translate industrial, scientific, and organizational strength into battlefield dominance. The German infantry confronting these munitions in December 1944 were encountering not merely new technology but a clear expression of American industrial and technological systems. The fuse's timing, detonating mere tens of feet above the ground, embodied the gap between German expectations and the realities of American capability, where miniaturized electronics and precise radio signaling enabled a level of precision previously unimaginable in artillery. This short distance between explosion and impact symbolized a much broader difference: the efficiency of an industrial democracy versus the limitations inherent in a totalitarian production system. Beyond World War II itself, the proximity fuse ushered in a new era in warfare, the age of intelligent munitions. Contemporary precision-guided weapons trace their heritage to the first implementation of compact electronics in these fuses. The principle of embedding smarts into ordnance, revolutionary in the mid-1940s, has now become a standard feature of modern military technology. Furthermore, the production methodologies developed for these fuses left an enduring mark on post-war industry. Stringent quality control, controlled environments for assembly, and meticulous component handling informed the early semiconductor and electronics sectors. The women who labored in these assembly lines were at the forefront of these techniques, laying the groundwork for practices still common in electronics manufacturing today. Organizational lessons from the proximity fuse program proved equally lasting. The seamless collaboration between academic researchers, industrial engineers, and military planners established a template for Cold War-era weapons development. The program clearly illustrated that a democratic society could harness science and industry for military innovation with an effectiveness that rivaled and in some respects surpassed that of totalitarian states. This account is based on verified historical sources and primary documentation. Production statistics are drawn from records of the Bureau of Ordnance, while technical details come from declassified Johns Hopkins Applied Physics Laboratory files. Combat observations are taken from official after-action reports and military histories. Unverified claims such as exact casualty numbers attributed to proximity fuses or reports of German electronic jamming efforts have been deliberately excluded as they lack concrete evidence. Some widely circulated narratives appear to be amalgamations of multiple events rather than precise historical occurrences. Nevertheless, the documented impact of the proximity fuse, both on the battlefield and on subsequent technological development, remains extraordinary. The introduction of the proximity fuse marked a fundamental shift in artillery technology, transforming it from a weapon of indiscriminate area effect into a highly precise instrument of combat. Its creation and subsequent large-scale production underscored the extraordinary capabilities of American industry during World War II. The deployment of these devices accelerated the defeat of Axis forces. At a mere 30 feet above the ground, the supremacy of democracy over fascism was demonstrated not solely through ideology, though though the United States maintained a moral high ground, but through the practical mastery of industrial efficiency. The proximity fuse, essentially a compact electronic mechanism embedded in an artillery shell, highlighted a critical misjudgment by Nazi leadership regarding the United States. Where Germany interpreted diversity and political openness as weaknesses, America leveraged these traits into a formidable capacity for rapid mobilization. Jewish scientists who had escaped persecution in Europe contributed essential expertise to the development of the fuse. Meanwhile, American women, excluded from direct combat roles, played a crucial part in assembling these advanced weapons that would decisively impact the battlefield. Despite the apparent inefficiencies of a democratic system, the United States produced millions of complex electronic devices, while Germany, operating under a centralized authoritarian structure, struggled to maintain even basic ammunition production. The German troops confronting proximity-fused artillery in December 1944 were, by most measures, elite combatants. They had survived countless campaigns across multiple fronts and dominated much of Europe. Yet, their skills and courage were insufficient against the leap in technology represented by the fuse. In the fleeting moments between detonation and impact 30 feet above their defensive positions, they confronted the reality that American innovation could outmatch traditional military expertise. The effects of the proximity fuse extended beyond the immediate casualties. It shattered entrenched military doctrines, the belief in the invincibility of fortified positions, the notion that personal valor alone could counter technological advances, and the idea that methodical, hierarchical control guaranteed battlefield dominance. Within these 30 feet, tiny radio sensors in the shell executed detonations with precision that German planners had failed to anticipate, demonstrating the capacity of a free society to conceive, engineer, and mass-produce revolutionary tools of war. Each fatal strike against German infantry reflected the tangible results of an industrial philosophy brought to life, not through theoretical discussion, propaganda, or ideological superiority, but through applied engineering, disciplined production, and technical ingenuity. The proximity fuse exemplified a synthesis of sophistication and scalability. It combined intricate design with the ability for mass manufacture, complexity with reliability, and high cost with expendability. Its lethality derived not from cruelty but from meticulous engineering. Battles were decided not through brute force but through calculation. Victories were secured not through intimidation but through the unmatched output of industrial systems. The confrontation of German soldiers with these weapons symbolized the encounter between established modes of warfare and emerging technological paradigms. Traditional defensive strategies perfected over centuries became obsolete almost instantly. Earthworks and foxholes, once reliable shields, could no longer guarantee survival. By December 1944, German infantry had only a few moments and a brief vertical space 30 feet before proximity-fused shells detonated above them. This short interval represented the collision of two eras, the conventional methods of the past and the technologically driven strategies of the future. Where soldiers measured survival in meters, American engineers measured effectiveness in megahertz. The new reality of warfare had arrived, meticulously designed, mass-produced, and executed with exacting precision, a mere 30 feet above the battlefield. The proximity fuse, in its unassuming yet transformative function, became the embodiment of democratic ingenuity applied to the grim necessities of modern conflict.